Great. So welcome everyone. It's a pleasure to have an actual in-person Marvel Distinguished Lecture. I noticed with pleasure that we reached the 37 mark, and we have here a long-term colleague and friend, Professor Massimiliano Di Ventra from the University of California, San Diego. Massimiliano actually is an EPFL alumnus. In fact, he received his PhD here in 1997, working with Alfonso Baldereschi, that very sadly just passed away last week, and he was actually an undergraduate supervisor for both of us. So after his PhD, Max moved to the United States. First, he was working at IBM and the University of Tennessee. Some of the very, I think, early accomplishment in transport calculation with Norton Lang and Sok Pantelides, and was the beginning of molecular electronics then. And then he started as a faculty at Virginia Tech in 2000, but moved soon after to UCSD in 2004, where he has been ever since 2006 as a full professor. Many awards, many talks, but especially many books. I was particularly impressed by your 5 books. And again, a pioneering effort in so earlier on electronic structural calculations for transport, for nano devices, sort of collaboration also here at EPFL on sort of DNA translocation through pores and sequencing. But I would say, major focus in the last few years, both on the research side and the technology transfer side, as we know, MemComputing. And so we'll hear the lecture today on MemComputing when memory becomes a computing tool. So Max, the floor is yours. Very much welcome.
Thank you, Nicola, for the kind introduction. And you will see me also moving. As you can see, this thing shuts off randomly. So I will move the slides a little bit. So it's not because I'm crazy, but because I try to keep it on. So as Nicola was saying, in the last few years, I've been working on a new computing paradigm that I call MemComputing, which is a non-Turing paradigm. I will be discussing what it is. And if you're interested, I wrote a book for Oxford University Press, which came out a couple of years ago. Most likely, you have it for free here at the university if EPFL has an agreement with Oxford University Press. If you're not interested in reading 380 pages of a book, then this is a Physics Today article I got invited to write. Also in 2022, that's 4 pages only, and so it's just a summary of the book. So this, I would suggest you start from this and then go into the book. Now, for full disclosure, I have a company which, with great imagination, we also call MemComputing. You can go on their website. They have the software as a service available, and they're going now, hopefully, for hardware. So a little bit of a context. Here is a graph that I actually found when I was preparing a new class on unconventional computing last year, where the Semiconductor Research Corporation shows the amount of energy that is consumed by doing calculations versus the world production of energy. And you see here that if this goes straight, as extrapolating this, it will cross the amount of energy that we need to compute will cross by 2045, around that time, the world's energy production. So we cannot continue along those lines. And SRC says that the market will limit. So probably there will be less videos uploaded on YouTube. I don't know, but something that has to happen. So the point that I want to make is that, yeah, you can come up with better systems, devices, less power hungry, and so forth. But I also argue that probably we should move away from the Turing paradigm altogether. And that's what I'm going to discuss. So changing completely the starting point. So the first thing is words. Mem. The mem here means memory. But by memory, I don't mean storage. In fact, it's the general physical property shared by any physical system, whether quantum or classical, such that if you perturb the system at a given time t0, the perturbation is felt at a later time. Or in other words, the state of a system at time t depends on the full history of the dynamics. So this is shared by any physical system, whether it's a quantum or a classical, precisely because you cannot respond instantaneously to an external perturbation. So any system has to respond with a time non-local response. Now, whether it is easy or not to detect that memory effect is a different story. But for the things we will be discussing, the systems I'm looking at are those for which this memory effect exists. So instead of calling memory effect in the physics literature, you would typically call it time non-locality. So as I said, the fact that the response is non-local in time. Okay, so that said, what is it useful for? So we are interested in solving tough real-life problems. And by tough, I underline tough because even problems that are typically classified as NP-complete, NP-hard by computer science, many instances are easy to solve. We're not interested in those because for those we have very good algorithms, and so there is no point. We're really interested in those that are tough, really difficult to solve with traditional algorithms. And these appear in a variety of domains, from logistic, transplantation, encryption, to artificial intelligence, machine learning, and so forth. And also in quantum physics, quantum phenomena, material science devices, and many other domains. My company operates mostly on this side of this slide, mostly on logistics, transportation. I will show you the factorization that they did, breaking of RSA, and a little bit of machine learning. And my group and I work mostly on the other side, most fundamental. And we have results on all of them. I won't have time to discuss everything, but I'll show you some results. So here is what the company has been doing so far with industrial partners and government partners. So these are the companies we can talk about. For others, we cannot because we have a non-disclosure agreement. So they worked with Lockheed Martin, Chevron, BP, and others. And a lot of funding comes also from the Department of Defense. For example, the factorization was funded by the Defense Innovation Unit we'll discuss. Okay, so let me step back and let's start from the Turing way. So how we actually solve problems using the Turing paradigm. So without going into the details, this paradigm that was actually introduced by Turing almost more than 80 years ago is a mapping between a finite set of symbols, typically zeros and ones, into a finite set of symbols. And in between is what the computer sciences call a transition function, which is an algorithm. So this is essentially what a Turing machine does. Now, it doesn't tell you why the problems are so difficult. And to do that, let's look at any of the problems that I mentioned before can be written typically as a collection of gates related to each other by other gates. So for example, if I have a gate, an OR gate that relates to three variables, V1, V2, V3, and they are related by some AND gates, you have a formula, a Boolean formula, right? So what you want typically is you want this to be true, right? Satisfies this formula. So you want to find the assignments V1, V2, V3 that satisfy this formula. So how do we do this in practice? Well, we randomly select typically zeros and ones for V1, V2, V3, and check literally every clause if it's satisfied, right? But here you see immediately that there is a problem, because if I check this one, I have to check also the next one, and the next one, because V1 appears in all clauses. If it doesn't work, you have to redo it by changing, let's say, V2 and redo this process, which is perturbative in the sense that you have to do it one step at a time, right? Until you check everything and you have hopefully solved the instance. Now, if you look at this not from a logical point of view, but as a physical system, suppose that these V1, V2, and V3 are actual physical objects like voltages on some actual hardware, right? You see immediately that the problem becomes tough because you have a long-range correlations between the variables. The variables appear at distant clauses, physically distant clauses, and so you need to literally know at once what's happening to all the other clauses. So in other words, instead of using our machines or any algorithm, it would be ideal to have a machine that has a long-range order, a machine that can see in some sense the entire problem at once. Now you see that this thing is, I'm no longer talking about speaking in terms of computer science language, but in terms of physics, right? So I'm looking at a physical object that actually showcases a long-range order. It discovers this long-range order while it's trying to solve the problem. And this is a non-perturbative type of approach, because long-range order is a strongly coupled physics, a type of strongly coupled physics, and so it's a non-perturbative. So that's where memory comes into play, the time non-locality. And why it is important? Because memory can create a long-range order. In fact, it's used already in nature. For example, if you know how ants solve the shortest path problem, they send out ants randomly, right? And they release pheromones, right? So they release a memory trace that can be followed by the other ants. So they reinforce the shortest path. So in this case, as in the machines that I will show you later, you have two types of degrees of freedom. The ants, which are faster than the decay of the pheromone in this search, right? And then you have the memory degrees of freedom, which are slower. So remember, you have two types of degrees of freedom. The fast ones, which are the ones that you are interested in, like the variables in the problem that was mentioned before. And then you have the slow degrees of freedom, which is the memory. And then when they start to reinforce the shortest path, at a certain point, they create a long-range order in the system, right? So they literally solve the shortest path problem by using memory, by creating long-range order. By the way, it's also very robust, because if you ever tried when you were a kid, if you perturb this thing, the ants will reroute the path and reform on the fly the path, right? It's very robust to perturbations. So this is indeed MemComputing in nature. Okay, so the goal for us is to find an actual machine or design machines that operate like the ants, where you have two types of degrees of freedom. The fast ones, which are the variables we want to solve, and the memory degrees of freedom, which are the slowest ones. Okay, so we are using now non-algorithmic methods, totally different. We want the physics to solve the problem for us. You start from an initial condition, you want to go to the solution, and you want to use non-perturbative approaches, and we will use memory. So as I said, this is a physics type of approach, and in fact, there is a famous quote by David Deutsch, one of the founders of quantum computing, that says the theory of computation has traditionally been studied almost entirely in the abstract as a topic in pure mathematics. This is to miss the point of it because computers are physical objects and computations are physical processes. What computers can or cannot compute is determined by the physics alone, the laws of physics alone, and not by pure mathematics. I fully agree with this. In fact, what I just showed is that we are moving away from computer science language and moving into the physics language. The question is, which type of physics are we going to use? And here you have two choices, right? You can use what is mostly done nowadays, which is quantum physics, or non-quantum physics, right? Now, I hope I'm not going to offend anybody doing quantum computing, but there are several issues with quantum computing. The first one is that a quantum computer operates with state vectors in a Hilbert space. And a Hilbert space has a dimension that explodes exponentially with the number of qubits, right? Which means that you cannot simulate these things on our traditional computers. You have to build these machines to see any advantage at all, right? And if you want to use features like entanglement, they are actually very sensitive to decoherence. In fact, the entanglement typically scales quadratically or cubically with the number of qubits. So as soon as you start the process, decoherence will destroy the entanglement. So they're very difficult to scale, and they're very limited in the type of problems they can solve. For example, Schur's algorithm is one of the few algorithms that can be adapted to a quantum computer. But it's very limiting to think that only quantum physics is good for computing, because we have an entire range of what we typically call in physics classical systems. I call them non-quantum because if you say classical in computer science, they mean Turing machines. And we're not talking about Turing machines. And quantum computing guys also think of Turing machines. So non-quantum or classical. And there is a huge difference because in classical physics, a classical system lives in a phase space, not a Hilbert space, which is, by the way, not linear like the Hilbert space, is a nonlinear space, but its dimension grows linearly with the number of degrees of freedom. This is an incredible advantage. Why? Because if you can describe them with ordinary differential equations, like the ones that I will show later, you can simulate them efficiently on our computers. In fact, what I will show you are essentially simulations of ordinary differential equations. We haven't built these machines yet, and they already show some advantages already by just simulating, not even building these things. Not only that, but what I will show you is a much broader type of computing paradigm. It is scalable because it's digital, I will show in a moment, and it is topological in the sense that it uses topological objects to compute. Okay, the other thing is that in quantum computing, you have to adapt the problem to the machine. That's the reason why we have very few algorithms that operate on a quantum computer. You have to really make it adaptable to the machine. We actually operate in the opposite direction. We want the machine to adapt to the problem. You remember, if I have a machine that can discover long-range order, it will adapt to the problem itself by discovering the long-range correlations between the variables. So that's the type of machines that we are actually looking at. And that said, any physical system actually computes, right? I'll show you ours. But if you take, for example, I use this analogy also later. If you take a pinball, right, and it's driven by gravity, and there are no local minima where it can get stuck, the ball has to get out, right? It has to get out at the bottom. And we actually can interpret what it does as a trajectory, although the ball itself does not know it's actually solving anything, right? It's actually doing whatever it has to do. If you put paint, for example, here, it will trace the trajectory. We can actually interpret that as, we humans interpret that as a trajectory, but the ball doesn't know it. So this tells me that a physical system has no choice. So if I actually design a physical system to do something, it has to do it, right? If I let the ball go down via gravity, it cannot just decide at midair to stop and say, okay, I'm not gonna go down, right? And the other thing is that the physical system has no knowledge about the difficulty of the problem. If you actually design it to solve problems that are very complex, right? Well, it has to do it because it has no other choice, okay? So remember this analogy because it will come handy later. So here is another thing that we need to decide. So the problems that I was mentioning before are classified as combinatorial optimization. What does it mean? It means that they have input and output, which are finite strings of symbols, typically zeros and ones. Now, this is an important property because if the input and the output were real numbers or complex numbers, like in quantum computing, then these machines would be analog because a real number or a complex number requires typically an infinite amount of bits to be represented, right? So what you want for a scalable machine is that the input and the output are digital in the sense that you can read and write those numbers with a finite precision, independent of the size of the problem you're trying to solve or the size of the machine. By the way, we do this also in our computers. We use physical objects, transistors, right? Where we represent a large current, a one with a large current and a zero with a low current. But of course, this cannot be done with a mathematical precision. So there is always an error in here. But the important thing is that that error does not scale with the machine itself or the problem that we are trying to solve. So that's the same exact physics. So we want to be able to read and write with errors that are independent of the size of the problem, so that we don't have issues with precision and the machines are digital, scalable. What you have in between is irrelevant. As long as it doesn't scramble the input and output, it's important to have input and output which are digital. And the other thing is that we want to be able to fabricate these things with present technology. We don't want to have fancy materials or new things that will be will take longer to fabricate. So this is these are the requirements that we want to have. And in between, as I said, we will use physics, the physics of memory or time and locality. By the way, if you have a question, they can interrupt, right?
It's
I don't know.
Yeah, I think we haven't
free.
done it in person in a while, so it's
okay.
always online.
Okay,
so
feel
just
free to
elicit the
interrupt
audience. Yeah.
So we define a new what we call universal MemComputing machines. Universal is because they are Turing complete. It means that any problem solved by a Turing machine can be solved by our machines. We couldn't prove the reverse because the definition we have has more physics into it. A Turing machine knows nothing about the history of the process. And apart from a control unit that tells the machine what to do and the input and output, everything is done in what we call computational memory. But again, we don't mean here storage, but time no locality. So objects that actually use time no locality to process. I'm not going into the details of this. If you're interested, you can look up at this paper. But the important thing is that you can define these things like Turing did with his machines so that you can prove theorems. So that's the whole point, right, of having these definitions. But as von Neumann correctly said, if you tell me precisely what it is a machine cannot do, then I can always make a machine which will do just that, right? I mean, a mathematician can always define a machine. And the question is whether this is only mathematics or you can actually build these things in hardware. That's the next step. Okay, so I told you that memory allows us to discover a long-range order, right, in a problem. But it can also allow us to do something else, which is the following. If you start again from the problems I was mentioning at the beginning, and you write them as gates, right, related to each other by some other gates. These are OR gates, for example. Suppose that this is a search problem, right? Suppose you know the solution, you can check it. In reality, what you want is you set all to 1, right? And you want the gates to self-organize to find the correct variables that satisfy that formula. What does it mean? It means that instead of having information flow in one direction, like a traditional gates, you need to have information flow also in the other direction. And those are what we call self-organizing gates. Okay, so the memory not only allows the system to create a long-range order, it allows us also to create a new set of gates, which we call self-organizing, and which are bidirectional. They allow information flow in both directions. Not one-to-one, careful, because this has 4 input terminals, 1 output, but as long as it is bidirectional, the flow of information is fine. So what do? We take any of those problems I mentioned before, and we write it either in Boolean or algebraic format. By the way, this is not even unique, depends on the problem, right? And we use those, which are given to us by mathematicians or computer scientists, and we take those circuits and we replace the original gates, unidirectional gates, with our self-organizing gates. And I'll tell you in a second how we make them. So suppose you have an AND gate, and this is the truth table, has only 4 logically consistent states. And the traditional gates can only do one thing, right? They can go from input to output. That's it. There is no other possibility. But now suppose I have inside here some physical degrees of freedom, memory degrees of freedom. So I transform this thing into a physical object that has only 4 attractors. These ones, they're the logically consistent states. So this is what we call self-organizing gates, because they actually operate irrespective of where the signal comes in, whether from the traditional input or the traditional output. Now, for example, if here I get a 1, I can design a physical system with the memory degrees of freedom that will give me only 1, 1 at the top. If I come here with a 0, I can design it so it will give me 3 possibilities: 0, 0, 0, 1, 1, 0. Which one will come out? Well, that depends on the initial conditions, because all of a sudden you are working with a dynamical system. So you have to set the initial conditions and the environment in which this gate operates, like the problem is trying to solve with the other gates. In fact, when you put it together, the memory does 2 things. It not only allows us to create these self-organizing gates, but it will create a long-range order once you actually start the dynamics at appropriate inputs, and then you read the appropriate outputs. So the memory does 2 things for us. One is long-range order, creates long-range order, and 2, it allows us to create a new set of gates.
Question.
Yes,
Max, what is the difference with reversible logic?
The Toffoli logic, right? That is a one-to-one.
Mm-hmm.
It's used in quantum computing, and it's one-to-one. These are not necessarily one-to-one. They are actually typically not one-to-one. They're bidirectional in the information flow, but we don't have the same number of inputs and same number of outputs typically.
So it doesn't preserve the local entropy.
That's right. That's right. Oops. Sorry. That's right. Toffoli gates are totally different. Now, here you can build these things in many ways. We started with electrical circuits just because they are easy to fabricate and scale. And so here is a gate with, let's say, the AND gate that inside has what we call a dynamic correction module. And let's say you represent a logical 1 with +1 volt, a logical 0 with -1 volt, whatever. It's your choice. And you see that this does not satisfy any of these 4 possible states. So this dynamic correction module, what it does, it reads the opposite terminals. It realizes that this is not in the right configuration, injects current so that this becomes 1 and it satisfies this. This one reads the opposite ones. It realizes that it's not right. It takes out current so it becomes 0 and satisfies this. And this will be done in real time, all of them, in this case 3, right, terminals. And again, which one wins? Well, that depends on the initial condition and the environment in which you put it. If you want to go in more detail, we started by assuming resistive memories and also active elements to do these things. But you can use standard transistors. You don't need any special devices or anything. We even have a paper where we just use the standard electronics because time and locality can always be emulated with transistors. And you can build all sorts of gates you want. You can build a XOR, an AND, an OR, whatever. And so these are the type of gates that we use, okay? And the memory allows us to do that. Now, here's the thing that I was mentioning at the very beginning. If you write down the equations of motion of these gates, well, they are essentially ordinary differential equations. They may be complicated, and in fact, we can simplify them as much as possible for the benefit of simulations, but they are ordinary differential equations with the fast degrees of freedom, which are the variables we're interested in, and the slow degrees of freedom, which are the memory degrees of freedom. So this is something we can simulate. It's not a quantum computer, right? This is a collection of ordinary differential equations. As complicated as they may be, but it's a collection of ordinary differential equations. In fact, these are nonlinear dynamical systems, right? With that can be simulated on our traditional computers, where the variables and the memory states are these things. So what did we do with this thing? We started from a discrete set of space, right? The traditional logic space, and then we made the zeros and ones continuous. And if you stopped here, you would have tons of local minima. So the problem with many algorithms is that they stop, and sometimes they use also continuous variables, but they stop at those variables. When you do that, you have plenty of local minima. Remember, like the pinball, they can get stuck if there are local minima. What the memory allows us to do is to transform those local minima into settled points. So at the end, you have only the logically consistent solutions of the problem you're trying to solve and settled points. So the system can always move downhill towards the exit or the point of solution. It's like, this thing, it's like the pinball, but in a much bigger phase space, right? Where the ball, between quotes, the trajectory of the system tries to find the exit, okay? Now, here you have 2 complications. One is that nonlinear dynamical systems not only have equilibrium points, which is what you want, but they may have also periodic orbits, right? Or quasi-periodic orbits, and chaos. So proving actually absence of chaos for our dynamical systems is actually easy, relatively easy. It's a topological feature. Proving absence of periodic orbits, no, it's not a trivial thing. In fact, we had to do it carefully for all the cases we looked at. So if you change the equations of motion that I was showing before, proving absence of chaos is relatively easy to do, but proving absence of periodic orbits, you have to do it case by case. Okay, the other thing is that if the system randomly goes through the phase space to find a solution, then it will be useless in the sense that it will be too long, right? Here is where we use a technique borrowed from string theory, supersymmetric topological field theory, without going into the details. It allows us to show exactly what is the dynamics happening microscopically in these machines. So the system starts from a random initial condition, and then it gets attracted to the closest settled point with some unstable directions, okay? Now, instead of wandering from there on, it actually can go through manifolds, which in field theory are called instantons, which are the classical analog of quantum tunneling. So they tunnel in phase space between quotes, to the next settle point with at least one less unstable direction. Why less unstable directions? Because these are dissipative systems and they will always go downhill. And from here, it will tunnel again to one less unstable direction, one less, and so forth until it finds the solution. The other thing is that the time reverse processes, the anti-instantons, are exponentially suppressed. These are dissipative systems. So even in the presence of noise, the instanton is the low energy dynamics of these machines. Not only that, but instantons, for those of you who know, are topological objects. You cannot destroy them or create them with perturbations. You see what I'm saying? You have to literally change the topology of phase space. So this dynamics is extremely robust against the local perturbations in the dynamics. And that's why, for example, we can simulate these highly stiff ordinary differential equations with a for Euler, which is the simplest method you can think of, but it shouldn't work, right, for this type of equations. The other thing that it allows us to do, I mean, this analysis in terms of instantons, we can literally count how many instantons we need to reach the solution. And you start from one random initial condition, you go to the closest critical point. The number of unstable directions of this cannot be larger than the dimension of the phase space. And if you remember, the dimension of phase space grows linearly with the number of degrees of freedom, not exponentially. And then the system goes via an instanton to at least one less unstable, a settle point with one less unstable direction, one less, until it finds the solution where you don't have unstable directions. So you can count these things and it grows polynomially with the number of degrees of freedom. Now, for those of you who think that this proves NP equal to P, this does not prove NP equal to P. So don't get a heart attack in this case. The reason is because these are physical objects, right, operating in continuous time. Turing machines do not operate in continuous time. They operate in discrete time. Now, if you can prove that the discretization of the ordinary differential equations we use do scale polynomially with the polynomial overhead, then yes, you would have proved NP equal to P, but we didn't, because for example, the topological field theory that I mentioned before does not apply to discrete systems. It applies only to continuous systems. However, it tells you also an interesting thing for mathematicians in the audience. I used counting instantons in a phase space is an exercise in algebraic topology. It tells us something about complexity theory. So it looks like there is a duality between these two fields of mathematics that would be interesting to explore. Okay, so that said, this is the theory. Let's look at applications just to see how far we can push it. So we start from a problem, whatever it is. Then we write it in binary representation, and we substitute the gates, the traditional gate with our gates. And then either you build these things, we haven't done that yet, or you simulate, which is what I will show, and then read the solution. So at the beginning, we thought that simulating this thing would not go that far, right? That our goal was to build these things, so like quantum computing. But as I will show you, for some problems that we already are better than standard algorithms by simply simulating differential equations. And that's what I will show, okay? So here is, for example, a factorization of 1073, which is 11 bits. The circles here are the zeros and ones that represent this number. Typically, I believe we used -1 volt for 0, +1 volt for logical 1. The dots are the input and output of the gates, which there's no longer an input and output for our gates. And black is 1, white is 0, and they continuously change, right? So if we switch on the inputs, I don't know if you can see this, but there are waves, which are solitons, which are instantons in one higher dimension. So the solitons or instantons try to push out the logical defects in this circuit until the system finds the solution. And if there is no solution, let's say you try to solve for a number which is already a prime, the machine never stops. So these are the voltages at the gates, and the spikes are the instantons, are not delta functions, and it will go on and on. So it looks chaotic, but this is a quasi-periodic orbit. So let's compare, for example, with the famous Scher's algorithm. N is the number of bits. The Scher's algorithm tells you that the machine is a probabilistic machine. You have to run it many times to get an answer. And it scales as n squared log n log square n for factorization on an ideal quantum computer, which means without decoherence. And then you have to do post-processing, also in polynomial time, on a traditional computer. This is the Schur's algorithm. If you use our machines, so those are deterministic. Noise is a nuisance, so it's not affecting too much the dynamics, and it's quadratic. Now, this is in hardware, okay, in continuous time. So it's not obvious that this thing is maintained by simulations, because in simulations, you have to discretize time. So you accumulate errors, and numerical errors are worse than physical noise because numerical errors accumulate. The physical noise is typically local in space and time. So this is the result from the company. I wasn't involved, but you can find the paper online. And they succeeded in actually solving RSA numbers. RSA numbers are those that we use for encryption, if you don't know, and in quadratic time. They stopped here literally because they ran out of money, because they were running on Amazon Cloud. But if this trend continues, they could, these are simulations, they could actually break 2048 in a couple of weeks or 3 weeks. And their code is a CAD, so they can actually estimate the physical time to reach the same solution. And if it again holds, then they could break RSA 2048 in sub-seconds. So now they're looking for money actually to build that. Yes?
I was wondering, what is this scaling of amount of gates that you need for this program?
Say it again, sorry.
What is the amount of gates that you need?
Oh, yeah, that's typically linear or quadratic, depending on the geometry of the system. Yeah, either linear, so if you write in conjunct in normal form, it's linear. If you write like this, it's quadratic. So number of gates is always polynomial. And the energy is always a scaling polynomial as well. Okay, so if you look at, if you're interested, this is the paper. Let me show you something that is more difficult. Actually, factorization is not even NP complete. So let me show you a 3-SAT, which is classified as NP complete. You have 3 variables per gate. And again, you need to find the instances that are tough, because you can find easy instances. So we took instances that are hard, satisfiable, typically used in competitions. And we used the 4 Euler implemented in MATLAB on a single processor, so not even parallelized. And in the main plot, you see log. These are our simulations. So these are the median of 100 instances per site, depending on the ratio between number of clauses versus number of variables. The most difficult ones are about 4.3, and they scale, in our case, cubically. In the inset, you have a log linear. So these are exponential. These are traditional algorithms. This is actually state-of-the-art, a message passing type of algorithm. And if you actually look at one instance, not all 100 median, one instance, it took about 15 hours, which is already incredible because we're running a 4 Euler. But if you actually extrapolated this, it will take over the age of the universe, literally. So this is an incredible advantage. We haven't even built them. So for certain problems, you don't need it. So to check that we are not deceiving ourselves, we gave our code to the Supercomputer Center for a test, and they used the MaxSat, which is, again, the goal is you don't have all the clauses satisfied, right? So you want to maximize the number of satisfied clauses or minimize the number of unsatisfied clauses. And this problem has what is known as an inapproximability gap, which means that up to a certain distance from the optimum, you can approximate it in linear time. Beyond that, it takes exponential time, unless NP is not equal to P. And so they use those instances and compare with the winners of this competition, which is by now it's old. But as you can see, the winners actually explode exponentially as a function of variables. This is the time to solution. And here is their solution, which is linear. In fact, if you extrapolate again, this one will take about the age over the age of the universe. One instance would take 2 hours on their CPU. The fact that they extrapolated this to the maximum number of ODEs that they could fit in their computer, and it's still linear. If you think it's incredible, because this is a 1 billion coupled ordinary differential equations running for Euler for essentially a day, and it still scales. which means it's very robust to noise, especially numerical noise. And they stopped there because they couldn't fit more. So in fact, the memory grows linearly, the memory for the simulations, and they couldn't fit more than whatever they had. So the last thing I wanted to show before concluding is that all of a sudden we have now in our hands a method to actually either find the optimum in a non-convex landscape or a good approximation of the optimum. Remember, in an optimization, we cannot check as a function of size, right, if we found the optimum, because it's the nature of the problem. We would have to compare with all the other sub-optima, and so it doesn't work. But for small systems, we can, but for large systems, you cannot. But what we show is that these machines can find either the optimum or a very good approximation to the optimum very quickly, which is the problem that faces machine learning. Remember that when you want to train anything like a restricted Boltzmann machine, you try to do this. These are essentially spin glasses, right? And you try to do it using gradient descent. Gradient descent is a local type of information. So they don't have information on the optimum, the ground state, which has global information, right? So by having a method like ours, what we can do is that we can combine standard methods with a sampling of the ground state or states of this highly non-convex landscape. So that's what we did. And here is a result. So for example, using restricted Boltzmann machines, you see that we can even reach KL divergence equal to 0, which means we can match the data distribution with an arbitrary precision with an error actually goes to 0, while standard methods could actually diverge. They don't actually converge. And the reason is precisely because we can actually match the modes or modes of the probability distribution very efficiently, while standard Gibbs sampling, called the CD in machine learning, gets stuck as soon as you have spurious modes. And in the case of deep networks, we did the same. And here are the state-of-the-art results. And you see that we can actually reach the same accuracy that Hinton reached with 500 by 1,000 nodes plus pre-training with just 120 by 18. So you see, if you have a global information on the system, which you don't have with gradient descent, then you can actually reduce the number of parameters to train the neural networks considerably. Here is 2 orders of magnitude. So that's an incredible advantage that we have now with this type of thing. So we can use this in many other contexts. Okay, so just the last thing in problems that we looked at so far. You can look up our papers or the company website. We looked at a random maxsat, maxcat, maxclick, all sorts. And the company mostly works in the integer linear programming domain because that's what industry requires. This is the 5th Airbus problem. It's an interesting story because Airbus put out 5 problems for quantum computers to solve if ever they're built. The 5th one is the loading optimization problem, cargo loading. And the company solved it, people at the company solved it in subquadratic time. Actually, it can be used now on the market. They submitted and it was refused because it's not a quantum computing solution. They said, go figure. It can be used in software. You don't even need the hardware. We looked at supervised learning. What I showed before is unsupervised learning. And we looked also spin glasses, quantum state tomography, ground state of correlated systems. So if you're interested, you can look up my papers or the book. And we have by now millions of instances between my group and the company. So it's not an accident. And again, it seems weird, but if you think about it, it's the physics that does the job for you. Whether you're at the end, you're discretizing, ordering differential equations, ultimately it's the physics that counts, right? And so if you represent those equations reasonably well, the physics will do the job for you. Okay, so in conclusion, we introduced a new class of machines we call MemComputing machines. They're universal in the sense that they're Turing complete and they can compute complex problems very efficiently. And you can practically build them. It's not just a mathematical concept. And the incredible thing is that not only you can build them in hardware, you can simulate them in software, which is an incredible advantage compared to quantum computing where you cannot do that. And it's very efficient and it's very versatile. So we don't have, I mean, we can solve a wide range of problems in the complexity, I mean, in combinatorial optimization class. And for them, in fact, you can use, as I said, simulations. So you don't need hardware, although hardware will be necessary if you want to, let's say, break RSA 2048 in real time. You need hardware. You cannot do it in software or other things. For example, autonomous vehicles, you need hardware. And apart from the applications, there is a lot of interesting physics in these machines. They share an incredible analogy with quantum chromodynamics. They're strongly coupled. The low energy dynamics is strongly coupled. The memory acts like gauge fields and the variables or voltages as matter fields. So there is a lot of interesting physics that parallels with the Yang-Mills theories, for those of you who know these things. So the people that actually did the work, the students, my collaborators, and Fabio Traverso, who was my postdoc and is now CTO of the company. If you're interested, again, the book has a lot of information. This is just a shorter version of the book. On the website of the company, you'll see the case studies. And with this, I stop and thank you very much for your attention.
Great. Thanks, Max, for the fascinating talks. For the people in remote, they can write on the question and answers pane, and then either Patrick sort of puts them online or we read the questions. But let's go from the room and Nanni.
Max, thank you for your talk. I've been following your research for years, and I find it always fascinating because there are things to discover and rediscover. Now, the question is following exactly in two parts. The first, you have a problem, and this problem you encode it as a logic network.
And there are many
gates, you know, what gates, you show as gates, and there are multiple ways of doing that.
Correct.
So question one is how you do it and what's the implication for that. And question two, which is coupled, is in the end, you have a dynamical system. And this dynamical system sort of is decomposed, or at least probably not totally, but partially into subsystems that correspond to the various gates. So probably the convergence, the speed of convergence, and the efficiency of your method depends also on the topology of the circuits that you start with.
Correct. That's a very good point. This is something we're starting to look at it now because, for example, we started to factor, and I have it even in a book, a factorization, and we did it with a SAT. So we're transferring into 2, 3, and 4 SAT. That's one way to write n equal to p times q, right? A factorization. It doesn't scale very well. I mean, it's still polynomial, but it's, I don't remember, 5th degree. And as soon as the polynomial is beyond 2 or 3, then it's still a polynomial, but it's useless, essentially, right? The company changed it into integer linear programming, and that scales very well. So what changes, right? So our hypothesis is that the local curvature of the unstable directions that could be affected by the topology, let's call it topology of the space, of the circuit that you're doing. So for example, if I have one representation, I need to be careful that these things do not become almost flat, because if they become almost flat, although they're saddle points, you don't get out pretty easily, you see what I'm saying? So what you can probably tune the parameters because we have 4 or 5 parameters, the company has other things. By making this again curved, but you have to work on it. So I suspect that the representation affects the curvature of the unstable directions, which are critical to get out of the saddle points as efficiently as possible. But this is something we're still working on. Does the answer?
Yes. Yes. Thank you.
Please. If you can press.
From some naive point of view, it resembles, let's say, analog computer with a kind of feedback between input and output. What is wrong here?
It's not analog because we read and write with finite precision, right? If you have an analog computer, it will not scale. Right.
But of this type.
The important thing is that the input and the output are digital. And in between, you have to have some, the transition function, let's call it transition function in computer science, has to be robust against noise, right? Whether it's numerical or physical noise. So this is very important, right? Because if this thing breaks, right, you wander in the phase space and it becomes a random type of search, then it's exponential. In fact, if I put too much noise, whether numerical or physical, this thing will break, right? And it will become exponential. But as long as you are staying within the manifolds of the instantons, which are topological objects, it's robust. It's robust to noise. So input and output are digital, and in between the transition function is of topological nature. That's the major difference compared to an analog machine itself. Yeah.
Thank you for the interesting talk. So I guess that the main problem that I see is those periodic orbits, let's say.
Yeah.
So correct me if I'm wrong, let's say, so my question is the following. So you could prove that there are, because I mean, if there is a periodic orbit, of course, you cannot reach the solution of the problem.
Right.
And so you can prove that there are no periodic orbits in some sub examples, let's say. So the way that I see, let's say, this technology to go is, you know, you have a very specific problem to solve. So it's like an accelerator in, let's say, in a GPU would work. So, I mean, you know, you have a very specific problem to solve that you know that there are no periodic orbits for, and you use this type of computing.
No, wait. Just let me stop you there, because the periodic orbits have nothing to do with the problem. They have everything to do with the equations you're using. So the physics of the gates, not of the problem.
I see.
That's the major difference. So for these equations, we have proved absence of periodic orbits. So let's say you change this thing into something else, you would have to reprove it. But that has nothing to do with the problem itself. You see what I'm saying?
I see.
With
So
the physics of the gates.
Okay. So thank you very much. So you're saying like it is, let's say, the property of the topological, let's say, physical structure of the gates.
That's
and
right.
You know, for the gates that you build, you don't have periodic orbits. So I mean, if I give you any problem, you'll find a solution.
Right.
The time for which you find a solution is the different thing. Let's say, correct?
The time yes,
that you find a solution is a different thing. Depends on the curvature.
Oh yeah,
let's
sure,
say, yeah.
Sorry.
But let's say
physical time.
the
right?
physical time.
The number of instantons will
But the periodic orbits are not there.
That's right.
Okay,
That's
thank you very much.
Now, in the original paper, we said, well, if you have a periodic orbits, right, if you cannot eliminate them, at least you have to make sure that the Bayesian of attraction of the equilibrium points scales reasonably compared to the Bayesian of attraction of this. In other words, this does not dominate. For example, I can change initial conditions, and even if this is present, I can always find this. As long as this does not dominate with increasing size, you're still okay. I mean, ideally, you want to eliminate periodic orbits, but if you cannot, let's say, right, for some reason, what you want to make sure is that the attractor of the Bayesian attraction of this is always greater than this, no matter is the size. Yeah.
Shout, maybe use the microphone. Just press the button.
Okay, thank you. So just for curiosity, basically these systems, the hardware, they are generalizing any type of linear programming scheme.
No, we can use those
Yes.
to do integer linear programming. Yeah, the company does. I've never done that. But
Okay.
The company does that.
Yeah, because
yes.
basically you search from the subset of solutions, right? The hardware,
Depends. The problem may have one solution or many solutions, right?
Yeah.
One attractor
Mm.
or many attractors, right?
Okay.
Depends on the problem. That depends on the problem, right? So let's say if you have a factorization, you have one solution, right?
Yeah.
But if I have a general problem like the 3 set, I may have more, several solutions that satisfy the same formula.
Yeah. Okay. Thank you very much.
Mhm. Yeah, the company is specialized in integer linear programming because that's what the companies want, right? So the SAS, the software services, is an integer linear programming code.
So, Max, as soon as a scientist has a toy, they want to break it. And so the question is, what does it take to break? And I was wondering, I mean, you need an adiabatic separation between the slow and the fast variables.
Not necessarily adiabatic, but I don't know if I have the slides here, but the noise can break it. So remember that this thing is a distribution, right? And this distribution actually is an inverse Gaussian. I mean, standard methods are all exponential, which means that they are typically, they become worse and worse the bigger the problem, right? But ours actually is different. So if you have a noise, for example, physical noise, you can prove that the distribution of the time to solution is an inverse Gaussian. And the relative variance goes to 1/n if the noise is controlled. But if the noise is too much, this coefficient again can go to 0. at that point, it becomes like a random search. You see what I'm saying? So if you have too much noise, it will destroy the whole thing. Yeah.
And maybe a last philosophical question. I mean, that if at the end we can do this on a classical computer, so why do we, I mean, is the physical paradigm just making it faster? I mean,
yeah, it's the physics that does it. Yeah, it's the physics. As long as, again, you have the right physics, the ordinary differential equations will represent that physics, right? Even if you discretize time, as long as delta t is not too big. Yeah, it's the physics that does the job. Yeah.
Cool.
And there's another question.
Please.
About the factorization.
Yeah.
So if I input, so let's say that we have a sufficiently large circuit, and if I input a prime number, then
It will never stop.
it will never stop. Do you have any idea about the period?
It's a quasi-periodic orbit.
Yes, but do you have any bounds on how long the period is?
No, the only thing we can say
that it's going to repeat.
Right, that we cannot. The only thing we can say is that it is an inverse Gaussian, the time solution.
Yes,
so you're asking, you can ask the question, if I have, let's say, if I'm here, what is the probability that the system does never?
Okay, I see.
That's because it's a physical approach, right? So it's like asking, with 5 sigmas, did we find the Higgs boson or not, right? That's the same thing. So that's the best we can do, right?
Okay, thanks.
Cool. We have a question from the audience that says, if the inputs and outputs are exchangeable, how the decision is done, that is, whether a link is an input and or an output, is it predefined in the DMMM?
Yes, those are fixed by the gates, right? So those are fixed by the gates.
And because the follow-up is deciding whether a link is input or output has to ensure that there are no loops, and the resulting logic is a directed graph at the end.
Not necessarily, because again, the graph is given to you by the type of problem you want to solve, right? And what you want to make sure is that whatever is your gate, it will always go to one of these 4, in this case, logically consistent things, and that's it. Then you put these things in the circuit that is given to you by the problem itself, and then that's it. The system finds the solution. So there is no cycle. It doesn't matter whether it is cycle inside or not. You see what I'm saying?
Yeah,
So
it's
that's
like being in a vortex in the middle of the ocean.
yeah, it will go no matter what. Yeah, I'm not sure I answered the question.
I think the technical word would be race. Whether there is a logic race in the circuit doesn't matter, because that doesn't affect the convergence.
Yeah.
Sorry for that.
No, that's fine. Thanks for clarifying this. Yeah.
Great. If there are no other questions,
Thank you.
Again, Max, a great pleasure.